Hello again, my dear student. Now it's part number 2 of our energy band diagram lecture, lecture number 3 in the solid state course. Okay, so this was our terminating slide by part number 1 when we studied the effect of applying an electrical field of the energy band diagram, and we understand that theory of what's called the minimum potential theory. Here, as you can see, electron will drift toward the right direction due to this positive terminal of the battery, while the holes will drift to the left direction due to the negative terminal of the battery. In the next slide, we have introduced some relations. As you can see here, I will also use my whiteboard to illustrate this relations, because again, this is a very important relations in our course. So, as you can see here, the energy, let's start to define some important parameter. So we have, okay, so we have the energy, we call it E, with the unit electron volt. We have V, or what we call it the potential, with the unit volt. We have eta, which is the electrical field, in the unit volt per meter. And we have rho, or what's called the charge density, with a unit coulomb per meter cube. So these are the 4 functions or the 4 parameters. We would like to link these parameters. So I will state some equations. Maybe from the first impression you will not understand these equations. However, I will do my best to make it more and more clear for you, these such equations. So what are the equations? The potential V equals to minus the energy, but times Q. This is volt and this is electron volt. Makes sense. I'm sorry. Let's skip this. It's the reverse. I'm sorry. Okay, so it's the right, the other direction. The energy equals to Q times the voltage. And as far as this is an electron, so we can write it like that, minus EV. What is important for me is V proportional to negative E. And this proportional constant is the E small, or the electron energy. I'm sorry. Wait, now this is better. Okay, so V equals QE. Very logic. This has a unit voltage, and this has a unit to charge or electron. So the output unit is electron volt. Makes sense. Again, using units. Now let me use my previous slides. I told you that electrical field equal to voltage over distance. So I can write it in this manner, that voltage proportional to, or I'm sorry, electrical field proportional to partial V by partial X. Again with a negative sign. So eta is proportional to partial E by partial X. And finally, the rho is proportional to partial eta by partial X, which is proportional to partial 2E by partial X squared. So let me return to my slides and try to understand these equations using my slides. So let's take this, for example, this energy band diagram, and let's consider this energy band diagram as our example. So we have an energy band diagram like this. This y-axis represents the energy. So I can represent the energy. This is X, and this is simply the energy. Okay, so as you can see, if I would like to plot the potential V, the potential V is minus the energy, so it will be something like that. Okay, does this plot, which is a potential, make sense? Let's see. Now, this is an energy band diagram. If I told you where is the positive terminal, you will say, okay, this is an electron. The electron will move in this direction. That means that this is a positive terminal, and this is a negative terminal. That's right, because hole will leave. Okay, so this is the positive terminal of the potential, and this is the negative terminal of the potential. So if you would like to plot the potential, you would say, okay, if this have zero potential, by this terminal, I will reach a potential, for example, equal V node, the battery, and this is the potential, which is typically the same like this. So here, this potential makes sense. This is the higher potential, and this is the lower potential, as you can see. Okay, the next step is eta. Eta is the slope of this energy diagram. So the differentiation of this energy diagram is just a constant. This is the slope. But please take care. Now, here the slope is, I believe the slope here is negative. So you will have negative constant like that. So here this is the potential, and this is the eta. And finally, what about the Q, the charge, the rho? The rho is the second derivative of the energy. So the derivative of this constant is simply zero. These are the four outputs we can plot. Okay, let's start to understand. Here we just make some sort of mathematics without understanding. This is the negative function, this is the derivative, this is the second derivative, that's all. But what are the physical meaning of this, that? Because the next step is that we are going to use it in solving a very important question. Okay, so what is the negative meaning of this data? First, here we understand, whenever you have this energy band diagram, so if you have an electron here, this electron will drift in this direction. That's why this is the higher potential and this is the lower potential. Okay. And whenever you have a potential, then you have an electrical field. This electrical field may be a positive or a negative. So why this electrical field is negative? Let's try to understand. Now, this is the electron motion. Then, what about the current motion? The current motion is in this direction. You believe that the current is a reverse direction of the electron. Simply, if you add a resistance here, and you plot it like that, you will automatically tell me, okay, the current is in this direction. Okay, what is this direction? This is the negative x direction. That's why this is a negative electrical field. So if the battery is reversed, so this is a positive, this is a negative, you will get a current in this direction, and this will be a slope, a positive slope, and then you have a positive electrical field. So now this is a sign of electrical field, and this electrical field is negative. Finally, the charge is equal to 0. Here you have to stop me, and you told me you are wrong. We have a charge. The charge is not equal to 0. I told you, yeah, you have a charge. But this is what we call a moving charge. What I mean? As you can see, this is a slider. So whenever you have a charge, this charge will slide automatically and go to the right-hand side direction. So no charge will be static. If I told you, do you have any static charge? What do you mean by static charge? I mean charge which is fixed in this place. We don't have. So that's why rho equals 0, as rho here is static charge accumulations. So as you can see, charge is equal to 0. That's true, because all charge will move in this direction. No static charge will exist. Okay, this is perfect. Okay, so let me assume that you are still not 100% convinced with what I'm doing now. So we have to go with a very important example, I guess. Okay, to go to this as an example, let me now return back to our presentation. Okay. Okay, here is our presentation. Let's turn the laser pointer. This is the example. This is actually an unseen, a previous year and an unseen example. I mean, only it's not directly the previous year, maybe it's 2 years ago or something like that, but it's an unseen example. Here, this is the energy band diagram. The first question is, please plot the energy, potential, electrical field, and charge. The 4 quantities I just plot in the previous example. So let's do it. Energy is a copy paste. It's very easy. It's a 0 effort grade. What you are going to do is something like that. You will just copy paste what is in the slide. That's all. This is energy in electron volt, and this is the x direction or the x axis. Okay, so here we have some labels. For example, this is L over 3, and this is 2L over 3, and this is L. Okay, then what about potential? Very simple. Please remember, V proportional to minus E. So it's the reverse of this function. Here is the bottom, here is the top, then this will be the top and this will be the bottom. So we'll have function like that. Of course, these are straight lines, and my drawing is not so good, so it's just a reverse function. Okay, so very simple like that. Just the reverse of the function. Here is the maximum voltage, and here is the minimum voltage. Okay, I need to check that I'm correct. Very easy. Insert an electron here. Assume that you have an electron here. So this electron will move this direction, and then here, then you have a positive terminal here, and the negative terminal here. Here is the positive potential, and here is the negative potential. Okay, let's plot the electrical field. So what about the electrical field? Okay, here you have a positive slope, a constant, and a positive slope. This is just the differentiation of this. So here you have a certain positive value, and then you have a constant. The differentiation of constant is typically 0, and then you have another constant value. Very easy like that. And finally, what about the charge? Oh, yeah, it's very easy. It's the derivative of this constant, which is purely 0 everywhere. So very easy, straightforward. Navigation doesn't include any sort of confusion. So just what you are going is the reverse function, then the derivative, then the second derivative. So here, just to remember, eta proportional to partial e by partial x, and rho is proportional to partial to eta by partial x squared. Very easy like that. Okay, so this is the first requirement in this question, was the energy band diagram. Let's go to what is next. What are the other requirements? I'm sorry. Okay, that's perfect. What are the other requirements in this question? Okay, I told you, please state when, or not when actually, where the material is an N-type and where the material is in a P-type, and where the material is intrinsic. Okay, N-type, P-type, intrinsic. To know N-type and P-type and intrinsic, we have to compare the Fermi level with the conduction band and the valency band. Where is the Fermi level? Yeah, this is the Fermi level. This straight line is the Fermi level. Okay, what about this dotted line? This dotted line, without mentioning, it's the intrinsic Fermi level. It's EFI. Why it's EFI? Because it's all the time, it's in between the Fermi band, the conduction band and the valency band. So this dotted line represents the Fermi level. The intrinsic Fermi level. Let me notate it. So let me use a pen now. So this dotted line is E. I'm sorry for this too bad handwriting. Fi. This EFI, this bad EFI, is the intrinsic Fermi level. So if here, what happened? Yeah, if in this stage, you can see that EF is higher than EFI. I mean, EF is closer to the conduction band rather to the valency band. So in this region, the material is N-type. Again, very bad handwriting. What about the other? In all this region, the material is P-type. Why the material is P-type? Because here, as you can see, the EF is below the EFI, or the EF is closer to the valency band. So in all this region, the material is a P-type. So here is the N-type, here is a P-type. What about the intrinsic? What is the definition of intrinsic? To have the Fermi level directly in the center of the energy gap. Here, can you see it? At this point, when EF overlap with EFI. So now the Fermi level is typically in the center, and at this point at x equal x node, the material is intrinsic. So it's an N junction from 0 to x node. At x node, the material is intrinsic, and from x node till the N, till L, the material is a P-type material. Okay, that's perfect. So let's go to the next. Let's clear our board first. Okay, what is the next question is? Okay, my next question is, does the material include any portion at which the material is degenerate? Okay, what about degenerate? What do you mean by degenerate? Do you remember the degenerate semiconductor? Yeah, this is the degenerate semiconductor. I'm sorry, yeah. Okay, when the Fermi level is too close to the valency band or the conduction band. So do we have a region at which the Fermi level is too close to the valency band or to the conduction band? Let's see. Okay, here. Can you see it? Let me annotate again. Okay. At this region, as you can see, typically at x equal L, the EF overlap over the EV. The Fermi level overlap at the valency band. Do you remember this point at which NA equals to NV? Is EF minus EV, it will be equals to 0. So we have what's called a overlapped Fermi with overlapped Fermi level with valency band. So this is another important example, my dear students. So this is another example. Perfect. Do you have more questions? Yes, I have. So what is the next question? So the next question is, can you determine the total energy of this hole? Can you see this hole? Can you determine the total energy of this hole? Okay, it's very easy. Now, my reference for holes are usually EV. So this hole has an energy equals to EV, and then it has an overall energy EV plus EG over 3. Why it's a plus? It's not a minus. Yes, it's a plus because the energy of holes increase by going downwards. So this energy is higher than the valency energy by a value called EG. Okay, what about the potential energy of this hole? Very easy. The potential energy of this hole is the potential energy of the state, including this hole, which is the valency band. So the potential energy equals to EV. What about the kinetic energy? Typically, is the remaining energy, which is EG over 3. So this hole has a total energy equals to EV plus EG over 3. A potential energy equals to EV, and a kinetic energy equals to EG over 3. Okay, then this is all we can do with this very important example related to the energy band diagram. I believe that in your in-class test, in your final exam, you will find somewhere a question dealing with energy band diagrams, because it's very important schematic or a very important approach with dealing either with material or later on devices. So an energy band diagram is usually will be your key point to understand any future device we will deal with. So this is a very important question. Finally, in order to terminate this part, I have to mention a very important question, which is what's called the thermodynamic equilibrium of a device. What is meant by a thermodynamic equilibrium of a device? A thermodynamic equilibrium is the condition at which no external effect is applied to your material. What is the sign for a thermodynamic equilibrium? The sign for a thermodynamic equilibrium is that you have a flat Fermi level. Whenever you have a flat Fermi level, then your device is under a thermodynamic equilibrium. Whenever the Fermi level starts to split, then it's not a thermodynamic equilibrium. So if I ask you in this question, does your device or does your structure is under a thermodynamic equilibrium, you will tell me typically yes, this device is under thermodynamic equilibrium. Okay, that's all for part number 2. It's relatively a short part where we deal with energy band diagram problems, a very important problem. Thank you, and see you with the last part in this lecture, which is part number 3. Thank you.